you may even go to farther than, that is, you can go to even higher energies. But you still remain within the closed darkness. Okay? Are they within the bounded darkness? Are they closed? That means, imagine we had this kind of picture. So this is my circular orbit, but I don't stay very close. Maybe I will go here. It is still bounded because I have two turning points here. It is still bounded, but is it closed? Okay? So we ask the question, and then the answer actually has to come from slightly more. So what we have to do is that the Taylor expansion of this J be truncated after first order in U minus U1. Now we have to keep more terms in that. So essentially I must write this J, or I should write this as d square x by d theta square plus x is equal to, earlier we had only x into j prime. Now I have to keep x square by factorial 2 j double prime plus x cubed by factorial 3 is 6 to j triple prime and so on. So I have to have other terms, higher order terms, and then probably we can neglect it. Okay. So this is a lengthy algebra, but I will try to just give some steps and then maybe I will conclude. And it's not it's available in the older edition Goldstein in the appendix, and I think in the new edition it is there are part of the chapter. So one can look at that one. So now we can. Let me just take this and then write it as plus beta square x is equal to already beta square x. We have already accepted beta square. Now here we have this x as cos beta theta. Now you have to write down, so you write down x as a function of theta into Fourier series of this type u1 cos beta theta plus u2 cos 2 beta theta plus u3 cos 3 beta. You understand why the algebra becomes more involved. And notice that as we go to the circularity condition, as we go closer and closer to the circular orbit, this term is the dominant solution, because we have seen from the previous case. So notice that u0, okay, so maybe this has got nothing to do with, these are just coefficients, okay, this has got nothing to do with the u or anything, so let me call as a0, j1,
Such a Fourier series.
just the Fourier series. So notice here that a0 and a2 are smaller than a1. a0 and a2 are smaller than a1. Why? Because when we go to circularity condition, this term survives. These two terms, all other terms will vanish. And a3 is much smaller than a0 and a2 itself. So this is the kind of picture that we have. So why I am giving this argument is because when I am taking x square and x cube, I am going to take square of all these quantities and then it becomes very messy. So what I want you to do is ignore cos 3 beta beta term. Ignore cos 3 beta beta term in x square. So I will have x square is equal to a0 plus a1 cos beta beta plus a2 cos 2 beta beta the whole square. This is my x square. When I am doing this x square, okay, neglect a0 square, neglect terms involving a0 square, a2 square and a0, a2. Why? Because their second order is small, already these are smaller than a1 and a2 square, a0, a2 will be second order. So I will neglect those terms involved. So as a result, what will happen? I will get my x square is equal to a0 square I will neglect, a1 square cos square beta beta, a2 square I will neglect, and a0 a1 plus 2a0 a1 cos beta beta, and a0 a2 2a0 a0 a2 I will neglect, okay, and a1 a plus 2a1 a2 cos beta beta cos 2 beta. So this is my x square.
A1 A2 will be then less than A0 A2, right?
No, a1 a2, see, a0 and a2 are small, so a0 square, a2 square, a0 a1 will be small, so I neglect. But a1 is appreciable because even for the circular orbit a1 is appreciable, so I cannot remove a1. So this is x square, and x cube, for x cube what I will do, so in x cube I will only retain this term. Okay, so we will retain so x cube is equal to simply a3 cube into cos cube 3 beta. Now we can write down several yeah. This sorry. Yeah, you're right. I don't keep
A1.
I keep only a1. Ask you a1. So I have my right hand side of this equation is a1 square cos square beta theta. I will write it as 1 plus cos 2 beta plus 2a0 a1 cos beta plus 2a1 a2 divided by 2 into cos beta theta into cos 2 beta. I can write it as cos beta theta plus cos 2 beta. Correct? So everything I have written linear in cos beta. So this quantity into j double prime by 2. Correct?
Cos 3 beta.
3 beta. 3 beta. And this term, so what will I write this term? Plus a1 cube into by 4 into cos cube, cos beta theta.
So the 3 beta cube.
Cos cube beta theta. That is, I am keeping only first term, the a1 term. So cos beta theta minus 3 cos beta theta minus cos 3 beta theta. Is that correct? Cos cube. What is cos 3 theta?
4 cos beta plus 3 cos
4 cos cube
beta
minus 3 cos beta. 4 cos beta. Maybe then this is minus and this is plus. So this is my right hand side. This into j triple prime divided by 6. So this is my right hand. And left hand side you can x is equal to a0 plus a1 cos beta theta plus a2 cos 2 beta theta plus a3 cos 3 beta theta. So if you write down dx by d theta or d2x by d theta square, I will get a1 beta square cos beta theta minus a2 4 beta square cos 2 beta theta minus a3 9 beta square cos 3 beta. So left hand side, so there is a naught here, so a naught beta square plus a1, so there is a1 beta square cos beta theta here and minus a1 cos beta, that will cancel, and I have minus a2 minus 3a2 beta square cos 2 beta theta minus 8a3 beta square cos 3 beta. So this is my LHS. So LHS and RHS have these quantities, and then you can actually combine them and collect the coefficient of cos beta theta, because in Fourier series these are linearly independent. So if you look at the constants, that is the term where there is no constant, there is nothing here, you have a1 squared by 2. So you have a naught beta square is equal to a1 square into j double prime by 4, or a naught is equal to a1 square j double prime by 4 beta. So this is one relation that you get by comparing LHS and RHS. Now if you look at the coefficient of cos beta theta, okay, cos beta theta, you have a term here, and you have a term here, and you have a term here.
That's plus 3.
Yeah, plus 3, yeah, and this is minus.
So both are
plus. So then I have, so in the left hand side 0. Okay, let us look at cos 2 beta theta. Cos 2 beta theta is a1 square cos 2 beta theta, and that's the only thing here. So a1 square by 2 into j double prime by 4. So that is a1 square j double prime by 4. And here I have, so this is equal to minus sign 3a2 beta. So a2 is equal to 12 beta minus a1 square j double prime by 12. So a0 is related to a1. As you can see that a0 is related to a1, a2 is related to a1. And then if you compare the terms for cos beta theta, this side is 0 because there is no cos beta theta term here. And on this side you have 2a0a1, 2a0a1 and plus a1a2 by 2 into j double prime plus 3a1 cube by 4 into j by 6. So that will be that is cos beta theta, and cos 3 beta theta you have minus 8a3 beta square here, and here you have one term here, that is a1 a2 by 2 into j double prime plus a1 cube by 24 j. Okay, so we have these four relations that we can get. Okay, so now I will skip some algebra and then tell you that if you choose the force, okay, you know that f of r we have written as minus k divided by r to the power 3 minus beta square. Okay, and from here you can write down j of u is equal to minus m by l square u square into f of 1 over u. Correct? This is our j of u. Now this u square I can write it as r square here, and so what happens if I do this, then this becomes so this f of 1 by u I can write it as plus k divided by r to the power 3 minus beta square. If I take this, this becomes minus 2, and that will give you 1 minus beta. So this is equal to mk by L square into u to the power beta square minus 1. So this is your j of for the kind of potentials that we showed that it is having so closed up. Now if you take j double prime and j triple prime and use these equations, j double prime and j triple prime, and use these equations, I will skip a lot of algebra in between, and then you will get the following condition: beta square into 1 minus beta square into 4 minus beta square. This is the condition
u power 1 minus u plus 4.
Huh?
U power
U power 1 minus. Okay, so this is the condition that you get for, that is, you use this J, find J double prime, and then substitute in these equations, then you will get consistency condition given by this. This essentially means beta square can be 0, beta square can be 1, or beta square can be 4. Now beta square is equal to 0 is, if beta is 0, what does it mean?
Constant.
Beta is 0 means there is no, it is not, it's not oscillating. So I require some non-zero beta. So non-zero beta, there are only two values. So beta square is equal to 1, beta square is equal to 4. If beta square is equal to 1, then in this potential, I will get f of r is equal to minus k by r square. This is our inverse square. Okay? And if beta square is equal to 4, then I will get 3 minus 4 is r to the minus 1 in the denominator, which gives you f of r is equal to minus kr. So these are the only two potentials that will have bounded orbits. However far they are from the circularity, they will always be closed. And these are the only potentials that have this feature. And this is Coulomb's force, the gravitational force, or Kepler's problem, and this is Hooke's law. So only these two potentials will have the so Bertrand's theorem answers this in completion, saying that if you are asking this question, that I want to all bounded orbits are closed. If you make this kind of a statement, it's true only for two forces. One is f of r is equal to minus k by r. Two, f of r is equal to minus kr. Okay, so this is the content of Bertrand's theorem. Finally, shows that only two possibilities are existing for force laws that are having all bounded orbits closed. But there are a large number of potentials. If you stay closely to the circular orbit, they will be closed. And all potentials which have this form. Okay. So let me also write this. However, potential force laws of the form f of r is equal to minus k divided by r to the power 3 minus beta square with rational beta have bounded orbits closed when the energy is close to that of circular path. So if the energy is close to that of the circular orbit, then these are all also closed. But if you don't have that restriction, lift that restriction, then only two possibilities are minus k by r. So this is any questions?